Okay. Last time we discussed the meaning of conservative force. Okay. The conservative force is a force that when you figure out the work, it is a different of a certain parameters or certain function, and that we call potential energy. Whenever the force is a conservative force, you can say that the work done is minus of the change in potential energy. So no matter how many force involved in this, if the force is conservative, this means that you have force 1, force 2, force 3, and so on. And then you write down that the force 1 is the change in the potential energy type 1. And then force 2 is the minus of the potential change in potential energy type 2. Well, you will end up that the total work by every force on one side, it is a change in kinetic energy. And on the other side, it is a minus of the change in potential energy. So by rearranging the term, we see that the potential energy plus all the kinetic energy plus all the potential energy is at initial point is equal to a potential kinetic energy plus the sum of potential energy at the final point. So you name the kinetic energy plus all the potential energy to be a mechanical energy. And then it's turned out that the mechanical energy of the system is conserved if the force is all conservative force. Now, you see that the type of force that are conservative is, for example, the first one, the force that are constant vector, such as gravity, gravity force on the Earth's surface. Well, it is mg, which is a constant vector. And we can prove that by moving the object from point I to point F in gravity in two different parts. The first part is the straight line directly goes from I to F. And the second part is a right angle part that from I to B and B to F. And it's turned out that with the constant vector force, the work done by both parts are equal. So that means that it's depending only on the initial point and the final point. And we see that it is actually mgh. H is the height of the object from reference point in direction of the gravity. So it turned out that for gravity such as mg, the potential energy can be written in form of mgy, and y or h is the height from the reference point. And then another form that are conservative is a force that depending on the function of x, y, or c only. There are no cross term. For example, in one dimension, you see that the spring restoring force is F equal to kx. Okay, and even though you have another terms involved, for example, plus bx squared in the x direction, it is still the only function of x only. So when you're doing a work done of f dot dx, you don't have any component on y-axis or on z-axis. So it is fx dx and fy dy and fz dz. Actually, in this case, let's add some more paper. Even if it is fx dx, fy plus fy dy plus fc dc, if the function along the x is the x only x, if function in x direction is depending only on the x-axis and y is still only on y-axis, or z is only the z-axis, this is also in a conservative force because it doesn't have anything that that different, that cross term. So, for example, that we're talking here is the elastic potential energy. Okay, where F equal to Kx. And you see that if force F minus Kx, you see that integration minus Kx dx, x and dx are in this, well, you can say that it is in y-axis in the same direction. So it's minus of xi to xf of kx dx. You can neglect the vector form, or you can say that cosine theta is 1. And it turned out to be 1/2 kxf square minus 1/2 kxi square. And this is only depending on position at the beginning and the position at the end. Okay. It is called elastic potential energy. To be ux, u elastic is 1/2 kx squared. And another form is the form that is 1/2 of r squared. For example, gravitational force. Well, this is actually the same form as the gravity, but in gravity we assuming that we are near the surface of the Earth, that the radial component is not quite different. So the gravitational force can be approximate to be mg. But if you're thinking about something like Earth and Moon or planet, the radial part is significant. So you have the gravity is minus g/m over r squared, according to gravitational attraction in the direction of r. And you're doing the integration also, and you say that work done by this gravitational force is a negative of some function at the final point minus some function at the initial point. And it turned out that the gravitational potential energy can be written in form of U equal to minus G, the large mass m and a smaller mass over R to the power of 1. And that is the gravitational potential energy when you're talking about the rocket shooting and some other words. Well, whenever we are inside the gravitational attraction, you see that it is minus g/m over r. It is a negative sign. So let's try something here. Okay. Let me pause the record for a few moments. And we can see here is the example. Of escape velocity. A rocket, okay, we can have some space here. The rocket launch from the surface of the Earth with velocity v are getting out of the gravitational pull of the Earth okay, and have velocity equal to 0 in outer space. Find minimum velocity that the rocket must have to leave the Earth. So here's the problem. On the surface of the Earth, you have a rocket that's going out with some velocity. Suppose it is 1. And then it's going out into space. Suppose outside they have V outside, V0, this is V0, let's say this is V, and it is equal to 0. But then it is escape the gravity of the Earth. So the question asks, what is the velocity v0? So we can say that by conservation of energy, total mechanical energy at the surface must equal to total energy at space. So at the surface, you have kinetic energy plus a potential energy at the surface. And this is outside, it is 1/2 mv squared in space plus the potential energy in space. Now the potential energy is, according to what we found from gravitational, is Gmm over r squared. No, not square, the 1. No, not highlight. Okay, for ME is the Earth mass, which is mass of the Earth is 6.4 times 10 to the 24 kilograms, if I'm not mistaken. No, 5.9. You can say 6. In 5.98. And mass of this is rocket mass. The radius, the surface radius of the Earth is 6,400 kilometers, or 6.4 times 10 to the 6 meters. So in outer space, if you say that you're getting out of the Earth gravity, you will see that the U is approaching 0. So we see that on the surface, This is mass of the Earth, mass of the rocket divided by R, which is the surface. This is surface. Potential energy. And this is surface kinetic energy. And outside, let's assume that this is 0. This is space velocity minus by gme over mlec over infinity, or this term approaching 0. This is out of gravity field. So you will end up that on the left side is 1/2 mv squared minus by g mass of the Earth m over r, radius is 0. And you can cancel the m out. So the v0 square is 2gm over r. I move the left to the right, the negative sign change. So the v is square root of 2gm over r. And that is, if you plug it in, 2 times 6.67 times 10 to the minus 11. Forget the unit. Newton meter square per kilogram square. And then you multiply with mass of the Earth, 5.98 times 10 to the 24 kilograms. And then divide by radius of the Earth, 6.4 times 10 to the 6 meters. Okay, let's see here. Two times 6.67 times exponential minus 11. And then times 5.98 exponential 24 divided by 6.4 exponential 6, and then take a square root. It is equal to 11164.5 meters per second, or approximately 11.2 kilometers per second. So make it 1,000 divide. This is what we call escape velocity. So if you want to send a rocket out to space, out of the Earth gravitational pull, you need to have a speed of the rocket at least 11.2 kilometers per second at the surface of the Earth, which is hard to get because you have to speed the rocket with a lot of acceleration at the beginning. So the way they did it is that they just increasing the speed of the rocket out into the atmosphere, and then using a second thruster to speed the rocket out into outer space with higher velocity. Well, most of the satellite doesn't have this much velocity because it is still inside the Earth gravitational pull. So this is not only the escape velocity of the Earth. From any celestial body, you can say that V escape is square root of 2g m over r. You can say that for the moon, it is much lower. So you can getting off from the gravitational pull of the moon easier. Okay. So here's the example of the conservative force. Now this is another example that we already discussed. Here's example 3, another one. I believe last time we spent too little time on it. A mass m is moving along x-axis with velocity u meter per second. It collides with mass large m, which is at rest and attached to a spring of stiffness constant k, as shown. Well, suppose the floor is frictionless and the two masses stuck together after collision. What is the maximum compression of the spring? And after the maximum compression, the two masses will move in simple harmonic motion. Find the frequency of oscillation. And C, write down the expression for simple harmonic motion of the two masses. Assume that the mass 1 is 1 kilograms. The last mass, capital M, is 5 kilograms, and initial velocity is 10 meters per second, and K is equal to 1,000 newtons per meter. Here we have, let's discuss this problem. We have 3 topics in one question. The first one is that the mass is moving and then collided to a second mass. Okay. And then the first one collide to the second one, and then it's moved together. So we are talking about collision in one dimension, conservation of momentum. So after the first mass collide with the second one, it is stuck together. The velocity of the total system is going to reduce, okay, according to conservation of momentum. And then if you compress the spring, so at that point, the kinetic energy of the total mass will transfer into the elastic energy of the spring. to find the compression. And then after the compression, the floor is frictionless, so the spring will push the mass back. And then it will undergo a simple harmonic motion. So you can find the frequency of oscillation of that. And then the maximum compression when from part A will become the amplitude of the oscillation. Okay, so they give you a numbers that the mass m1 or small m is 1 kilograms, the mass m2 is 5 kilograms. Initial velocity is 10 meters per second and k is 1000 newtons per meter. So let's take a look at this. Well, before the collision, okay, before the spring is compressed, it is a collision problem. So small mass m is colliding to the capital mass big M, where the large mass is at rest. So we have conservation of momentum, mu plus big M times 0 equal to the total mass times v. So after the collision, the whole system going to the right with the velocity v equal to mu divided by small m plus big M. And plug in the number, the small mass is 1 kilograms and large mass is 5 kilograms, and the initial velocity is 10 meters per second. The final velocity is 10/6 meters per second. Now, the object will compress the spring. In the beginning, the spring is stretched, so there are no elastic potential energy. But when the spring is compressed, the kinetic energy is transformed into elastic potential energy. So we have at point 1 the total of kinetic energy and point 2 the total of elastic potential energy. So we have 1/2 total mass m times v squared equal to 1/2 of kx squared. And you will see that if we plug in the velocity, which is small m times u over m plus m, or you can just plug in the numbers 10/6 squared, and you will end up that 1/2 and 1/2 will cancel each other. Let me take off this pen. Okay. Or 1/2 and 1/2 is canceling out each other. Let's change it back into point. So 1/2 and 1/2 cancel. M plus m and m plus m cancel by 1 terms. So we have m squared u squared divided by capital M plus m small m equal to kx squared. So x squared is m squared u squared divided by k m capital M plus small m, or x equal to mu divided by square root of k m plus m. And then you substitute by number. Okay. Let's get to this. And let's do this. X is equal to 1 times 10 divided by 1,000 square root of k is 1,000 times 6. K 10 and 2 of this. So it is x is actually 1 over square root of 60. Which is 0.13. Put it number, it is 0.13 meters or 13 centimeters compression. The spring will compress by 13 centimeters. And then after maximum compression, the spring will push the mass out and then going to simple harmonic with amplitude equal to x or 13 centimeters. And then the frequency will be square root of 1,000 over 6. And it is 12.9 meters radian per second. This is another zero here, radian per second. And so the displacement xt will be 13 centimeters cosine of 12.9 t meters. Centimeters, this is in centimeters. So that's the answer of this problem. Now, the question is, if we have friction force, well, a friction force for static friction, you don't have any movement, so there are no work done by the friction force or by any forces, whatever, because everything cancels out. You don't have the movement, so by definition of work, you don't have any work. So the work done by friction force will appear when you have the object moving. So it is considering only the kinetic friction. However, the friction force always opposite to the displacement. So the work of friction is always negative. It's always negative. So in that case, you cannot have a conservative force out of the friction force. So the friction force is considered to be a non-conservative force. So when it's non-conservative force, whenever there is a friction involved, the initial mechanical energy and the final mechanical energy will not equal, because it has some energy loss in between. But we can assume, or using a concept of conservation of energy, to say that the initial velocity, the initial mechanical energy is equal to the final mechanical energy plus energy lost by friction. So if there is a net friction involved, you see that the initial velocity will equal to the final energy, sorry, initial energy equal to final energy plus energy lost by friction. And then, for example, this problem, mass m is moving with speed u up the inclined plane. Let's say up the inclined plane with coefficient of kinetic friction mu k. How far it can go up the plane. So you see that it starts with at the bottom with the speed u, okay, and it stops at the height h from the ground. Well, if the inclined plane doesn't have friction, you can just say that the kinetic energy of the mass at the beginning will change into potential energy. So it is at initial point you have E1 equal to 1/2 mu squared. It's only kinetic. And the final point it is only mgh. It's only potential energy. Suppose you don't have a friction, these two will equal. So you will have the 1/2 mu squared equal to mgh. And you can find the h directly. However, in this case, we have the friction on the floor. So how much is the friction from the vector force, the weight mg is pulling down? You can break it into two terms. The one that pushing on the floor is mg cosine theta. The one that pulling back down is mg sine theta, and the other one is normal. And the friction is actually proportional to normal force, so it is mu n. So the friction force is mu mg cosine theta, and it is point downward because the object is going to move upward. So it will move by a distance of the hypotenuse of this right triangle with the edge, height h. So the energy loss is minus mu mgx cosine theta. Okay. Well, because mg cosine theta is the force that friction force mu mg cosine theta, and x is the distance. So we have 1/2 mu squared equal to mgh plus mu mgx cosine theta. Okay. It is a plus sign because it's at the magnitude of energy loss. Okay, so we can cancel the m out, and then you can pull out the x. By changing the h, let's detour a little bit. Because according to the triangle, the object moving up the ramp by distance h, x, to have the height h. So h over x is sine theta, or h is x sine theta. So we can put h equal to x sine theta here. So we have u squared over 2 equal to x times g sine theta plus mu g cosine theta. And the distance that going up the ramp is mu u squared over 2g sine theta plus mu cosine theta. Okay, this is just only waiting for numbers to put in. So let's suppose that the object has initial velocity of 10 meters per second. have the angle theta of 37 degrees and mu k of 0.8. And you will see that the x is 4.03 meters. Okay, by multiply u square is 100. 2g is 10, and then sine 37 degrees is 0.6, and 0.8 times cosine of 37 degrees is also 0.8. And plug in the numbers and you get the result. So this is some more complex problem. Okay, let's read this example. I will discuss it later. I will take a break for about five minutes. And today we're gonna have the quiz on simple harmonic, because tomorrow, I just realized that tomorrow is a holiday, so we don't have class tomorrow. We will see each other again on next Tuesday. So let's take a brief break to read the question, and then you can try working it out. I will discuss it later. Okay, take a 5 minutes break. Recording. This is another, let's see, another example of a application of conservation of energy. It is about the roller coaster that we call loop the loop. Possibly you played it sometimes when you visit the amusement park, maybe Dream World. It used to have at Dynamic across from Central Lad Prouth, but that place is closed for more than 10 years. The loop is a roller coaster that going around in circle, and there is a point where you flip upside down. Okay. Now, in order to complete the loop, the roller coaster must have some initial velocity that enough to push it across the loop. Okay. For this, in this case, so the roller coaster come down the top of the hill at height h, and then it's going to the ground, and then to reach the maximum velocity, and doing a loop in a circle of radius r to complete the loop. It's going out. So the question asks, what is the height h that the train can complete the loop? Now, in order to complete the loop, okay, the train must have reached the point B with some velocity. It cannot be stopped at B, otherwise it will fall. So when it reaches point B, it must have some velocity enough to maintain in track. And according to Newton's law at point B, you see that according to Newton's law at point B, suppose the train is here with some velocity. You will see that the mass, the weight of the train is pulling down by mg, and there is a normal force of the train that compresses to the track. And these two forces together acting like a centripetal force for its uniform circular motion. So at this point, we got mg plus n equal to mv squared over r. Well, the faster the speed, the stronger the normal force, because when the train reaches here, it's try to going into the straight line, and then it's compressed to the ramp, and then the normal force appear. So the minimum velocity that the train can have on this ramp at point B is when the normal force equal to 0, only the weight is pulling it down. So at this point, mg equal to mv squared over r, or the velocity is g times r. So the minimum velocity at point B must be equal to square root of gr. In order to the train to complete the loop. Okay. If the velocity is lower than gr, it will not complete the loop. It will fall down. But if it exceeds square root of gr, the train will complete the loop with people on the point B feeling some compression force, which is according to amusement park, they don't like it. They want the people on the train to experience a fraction of a weightlessness at this point. So they want you to have at least mg velocity equal to square root gr at this point. So by using conservation of energy, the energy at point A, which is on top of the hill, is 1/2 mgh without any initial velocity. At point B, you have 1/2 mvb squared kinetic energy plus mg times 2r as a potential energy. Now the minimum value of VB is square root gr. So VB squared is gr in order to complete the loop. So we have mgh equal to 1/2 mgr plus 2 mgr. M and G cancel. So you have H equal to 2R plus R with 2. So it is 5R with 2, or 2.5 Rs. And that means that in order to complete the loop, the train should come down with the height of 2.5 times of the radius of the loop. So if the loop have the radius of 10 meters, okay, the train will go down from 25 to 0.5 of the radius. So it's 25 meters to complete the loop. Okay, this is another example of conservation of energy. So let's keep this, and I will send you a here's a link to the quiz today. Let's go ahead and having the quiz. Today is about harmonic motion. There are 5 problems in all, and we have 20 minutes left. Let's see if you can finish it within 20 minutes, and I will prepare for the next class on next Tuesday. Okay, and I also paste the link of the YouTube on the 2304-155 Essential Physics BSAC page, and you possibly can reach it and use that connection to get to the YouTube. Okay, let's take our quiz.